Welcome to today's video on the cosmic age of the universe. The age of the universe is long. To put it into perspective, on a 1-year cosmic calendar, your entire life would pass in under a quarter of a second. Cosmic time just means time since the hot beginning, measured by a clock drifting along with the average expansion of space. A light year is a distance, not a time. It's how far light travels in 1 year. About 9.46 times 10 to the 15 meters, or around 6 times 10 to the power of 12 miles. The best current approximation for the age of the universe is about 13.8 billion years. Which, if we write in scientific notation, is about 1.38 times 10 to the 10 years. So it's easier to compare with other huge numbers. We need scientific notation because we'll talk about atoms, people, stars, the universe. And powers of 10 keep our thinking honest and compact. You'll hear expansion rate. In plain language, for every chunk of distance that already exists between two faraway galaxies, a little extra distance is added each second. Think of it like an interest rate on distance. More distance now means more new distance per second. Concrete rule of thumb using light years only. For each million light years, at about 22 kilometers per second of moving apart speed. So two galaxies 10 million light years separate at roughly 220 kilometers per second. And at 100 million light years, it's roughly 2,200 kilometers per second. The further, the faster. This does not rip apart solar systems or you in your chair. Local gravity and other forces win on small scales. Expansion shows up over huge intergalactic distances. How can expansion tell us the age? We measure how it changes with what the universe contains, then carefully rewind the movie back toward the beginning. To rewind responsibly, we need good distances and good clocks. So scientists build a distance ladder and use several independent clocks to cross-check one another. Distance ladders, well, step 1 is parallax, which uses pure geometry. We watch a nearby star shift slightly against background stars as Earth moves. The tiny angle tells us its distance. Step 2 is standard brightness objects, which make a reliable yardstick. Some stars and some stellar explosions have known true brightness. If they look dim, they're far. If they look bright, they're closer. We'll save the star physics for another video. For now, no yardsticks are calibrated by parallax, so we're not guessing. Independent clock A, rewinding expansion with those distances, you get an age near 13.8 billion years. Clock B, the microwave afterglow, the universe's baby picture, is detailed, pattern acts like a timestamp and lands on the same 13.8 billion years. The oldest star clusters set a hard limit. They're about 12 to 13.5 billion years old. So the universe must be older. Clock D. The cooling embers called white dwarfs, which we'll talk about more when we talk about stars. Their temperatures and faintness map to similar ages in the oldest groups. Radioactive element ratios in very old stars, another independent tick-tock that agrees with the rest. When different methods using different physics point to the same age, our confidence grows. That's science's multiple witnesses approach. A helpful clarification about size and time. The observable universe is larger than 13.8 billion years in radius, because space kept expanding while the light traveled. So what this really means is we don't know how much the actual universe, how big the actual universe is. We can only determine how big the observable universe is. But it's very likely that there's a universe beyond what we can see. Let's break any intimidating words before they trip you. Expansion, new space appears between faraway places, so their distance grows. Redshift, as space expands, light's waves stretch longer. We see that as redder. Parallax, distance from a tiny apparent shift because we view from two sides of Earth's orbit. Uncertainty, the honest plus or minus range on every number. Precision. Uncertainty is not a weakness of science, it is a strength of science. Keep units clean and familiar as you listen. Distances in light years, or meters if you want precision, times in years, speed in meters per second or kilometers per second, which is 1 kilometer per second is 1,000 meters per second. Here's how these scales fit in your life. If we compare the universe into one calendar year, compress the universe, your whole life fits into 0.18 seconds just before midnight on December 31st. Short doesn't mean small. Meaning grows when we place our brief minutes inside of a long story and ask better questions. In school, in health, in money choices, the cosmic method still helps. Trust conclusions most when independent lines of evidence agree, and use orders of magnitude to see what really matters. And the closing hook to anchor to your memory and your heart. On the longest timeline we know, you are a lightning fast spark, brief, bright, and uniquely able to understand the dark. Spend your seconds well. Quick recap. Cosmic time refers to the time since the hot beginning. The best estimate that we have for the age of the universe is about 13.8 billion years. Expansion, rule of thumb, the further the galaxies, the faster they separate. About 22 kilometers per second added for each million light years of distance. How we know the age? Well, many independent clocks agree. Rewinding the expansion, the cosmic microwave background timestamp left over from the beginning of the universe, the oldest star clusters, white dwarf cooling, and radioactive element ratios. The more independent results that point to the same time allow us to be more confident with the evidence. Horizons. The observable universe grew since ancient times, but accelerating expansion means the far future sky will empty as distant galaxies slip beyond view. We use scientific notation because it keeps cosmic scales readable and honest. With it, we can compare atoms, people, galaxies, and the universe using powers of 10. On a 1-year cosmic calendar, your life is fractions of a second. So use your seconds well. Think in evidence, compare independent clues, and mind the right scale. Let's look at a diagram showing cosmic time from the beginning to where we are today. Hello everyone, welcome back. I wanted to go over this with y'all so you could see exactly the cosmic time from the beginning to now. So as you could tell, on the very left, the little vertex of the whole graph is where you will see the Big Bang. So that happened at 0 time, 0 seconds. Again, as I iterated in class, we don't know exactly what happened in the first fractions of a second, but this model really, the physics that we have is enough to explain up to just a few of those from now all the way back to the first few fractions of a second. So the theory is the Big Bang happened, the universe started expanding extremely rapidly, as you could see by this, by the slope of the lines coming out of the Big Bang. And then at some point, about 380,000 years into the age of the universe, we have light is actually able to flow through the universe. So the universe becomes transparent. We're able to see, I mean, not we, because we're not around yet, but the universe becomes a visible place. Then it undergoes a very slowing expansion, right? We have different ages of the universe, so we call these the dark ages, from 380,000 to about 200 million years, because the first stars didn't form until about 200 million years. And then we, from 200 million years to about 1 billion years, we call this era the reionization era. And basically that's the first stars, from when the first stars formed to when the universe became ionized. Then from 1 billion to 2 billion, that's really, it was still ionized, and things were still expanding at a slower rate. More galaxies and stars were forming. And then we reached a peak of star and galaxy formation, which is also referred to as the cosmic noon. This happened around 2 billion years. And then just fast forwarding all the way to now, which is about 13.7 billion years. The universe is actually accelerating. The expansion of the universe is accelerating. So, yeah, this is this graph. It was created by the European Space Agency, so thank you, ESA. And I hope everybody learned something. Thank you.